What specific problem does TRELAWNEY aim to solve regarding next token prediction and teacher forcing in sequence models?
TRELAWNEY aims to address the limitations of next token prediction, NTP, and teacher forcing in sequence models, particularly their inability to learn long-range dependencies and the issues of error accumulation during training. Teacher forcing can lead to models relying on local patterns, resulting in problems such as the clever Hans cheat, where models simply copy easy tokens without understanding the underlying structure. TRELAWNEY introduces a data-centric approach by augmenting the training data with special look-ahead tokens that encapsulate future information, thereby facilitating the model's ability to plan ahead and learn critical early decision-making. This method allows for improved task performance in complex domains by decoupling the training objective from the data generation function, ultimately enhancing the model's capacity to generate long-term goals and improve planning.
How does the proposed method TRELAWNEY work? Please illustrate step-by-step the mechanism of data augmentation with examples of token interleaving.
The proposed method TRELAWNEY works by augmenting the training data through a process of token interleaving, which introduces special look-ahead tokens, less than t greater than and less than t greater than, into the sequences. This augmentation begins by selecting a decision point, D, in the sequence and inserting a sequence of K tokens, denoted as Z equals Z_1, Z_2, L dots, Z_K, between the special tokens. For example, if the original sequence is Y equals Y_1, Y_2, L dots, Y_T, the augmented sequence might look like Y equals Y_1, Y_2, L dots, Y_D less than t greater than, Z_1, Z_2, L dots, Z_K less than t greater than, Y_D plus 1, L dots, Y_T. The content of Z can be a copy of future tokens from the sequence or a strategically chosen subsequence that represents a future goal, which helps the model learn long-term dependencies and improves its planning capabilities. This method allows the model to receive a stronger learning signal for critical early decision-making, as it is guided by the future context encapsulated within the look-ahead tokens.
Can you provide a concrete example of how TRELAWNEY modifies a training sequence and explain the impact this modification has on long-range dependency learning?
TRELAWNEY modifies a training sequence by inserting special look-ahead tokens, less than t greater than and less than t greater than, at a selected point within the sequence, followed by a subsequence of future tokens denoted as Z. For instance, in the star graph task, the model might receive a prefix that includes the start node and a subgoal represented by a contiguous subsequence of future tokens, which guides the model's planning. This modification compels the model to generate a meaningful intermediate plan, rather than simply copying the ground truth prefix, thereby providing a stronger learning signal for critical early decision-making. As a result, the model is better equipped to learn long-range dependencies, as it is trained to consider future information explicitly, which helps it avoid pitfalls like the clever Hans cheat and the indecipherable token problem. Consequently, this approach enhances the model's ability to plan ahead and improves overall task performance in complex scenarios.
What are the theoretical or practical benefits of using TRELAWNEY compared to traditional next token prediction methods?
Theoretical benefits of using TRELAWNEY include its ability to enhance the model's learning of long-range dependencies by embedding future information directly into the training data through special look-ahead tokens, which contrasts with traditional next token prediction that often leads to local pattern learning. Practically, TRELAWNEY improves task performance in challenging domains, such as planning and algorithmic reasoning, by decoupling the training objective from the data generation function, allowing for better guidance in generating sequences. Additionally, the method enables fine-grained control over long-term generation, as users can specify future goals, which is not feasible with standard next token prediction. The augmentation schema also mitigates issues like the clever Hans cheat and exposure bias, which are prevalent in teacher-forced training, by providing a stronger learning signal for critical decision points. Overall, TRELAWNEY's data-centric approach results in improved model performance and planning capabilities compared to traditional methods.
How was the Trelawney method validated in the experiments? Please discuss the datasets used and the performance metrics that were considered.
The Trelawney method was validated through experiments on 3 types of tasks: synthetic benchmarks, star graph and algorithmic reasoning, and conditional story generation. For the star graph task, the dataset consisted of 200,000 examples generated programmatically, where the model was evaluated on its ability to generate paths from a start node to a goal node, with performance measured by accuracy against ground truth paths. In the algorithmic reasoning task, specifically the strongly connected components benchmark, the model was trained on 60,000 examples, and evaluation was conducted on 500 held-out examples, focusing on the accuracy of the final answers generated. Performance metrics included the accuracy of generated paths in the star graph and the correctness of answers in the algorithmic reasoning task, with comparisons made between models trained with Trelawney and those using standard next token prediction. Additionally, the experiments assessed both standard autoregressive generation and less than t greater than generation to evaluate the model's ability to generate plausible future goals and improve planning.
What significant results were obtained from TRELAWNEY's application in the experiments, especially in relation to planning and algorithmic reasoning tasks?
The application of Trelawney in the experiments yielded significant improvements in both planning and algorithmic reasoning tasks. In the star graph task, models trained with Trelawney demonstrated enhanced autoregressive generation capabilities, particularly on longer paths, indicating that the model could generate its own subgoal sequences effectively. The Trelawney random variant outperformed the fixed variant, suggesting that the flexibility in future goal selection allowed for better learning representations. In the algorithmic reasoning benchmark, Trelawney random consistently improved performance over next token prediction, particularly in less than t greater than generation and standard autoregressive generation, highlighting its effectiveness in guiding the model's planning process through meaningful intermediate reasoning steps. Overall, these results suggest that Trelawney facilitates better long-term goal generation and planning in complex tasks.